Hello everyone, today is day 15 of solving a LeetCode problem every day. So today I'm solving MinStack. I'll be doing something a little different. I'm just gonna go ahead and solve the problem and try to explain my thought process while I'm doing that. So the problem is called MinStack. So design a stack that supports push, pop, top, and retrieving the minimum element in constant time. So MinStack initializes a stack object, push pushes an element onto the stack, pop pops the top of the stack off, top returns the top element on the stack. Then this is like the little twist that this question is adding. Get minimum should retrieve the minimum element in the stack, and you must implement a solution with linear time complexity for each function. So I mean, if this requirement wasn't here and it didn't have to be in linear time, an easy way to do this would just to have a separate array that stores all the values. So that stores all the values that we push onto the stack, and we have to make sure that this array is sorted at all times, because then what we can do is just um, we can have it sorted in reverse order and then just pop the top of the array off, if that makes any sense. But that won't work for this current case because we want this to be in linear time. So this is what I'm gonna do instead. I'm gonna define, or I'm gonna initialize a stack, but what I'm also gonna do is initialize a min stack. And what this min stack is basically gonna do, it's gonna hold minimum values for the stack. And basically the top value on the stack is gonna be like the most minimum value in the stack. And then if you pop that, it's going to be like the next minimum value, and so on and so forth. It'll make more sense in a second, because the thing is we're not adding every element into this min stack, but it will make sense as we go through some test cases. So what I'm gonna do next is implement the push method. So when we're pushing, there's gonna be a couple things that we have to account for. So first of all, if the length of the min stack is empty, that means we haven't pushed any values onto the stack yet, and we don't have any minimum value yet. So what we want to do is just push this current value onto the minimum stack. So we're going to push that. Otherwise, so the other case would be that the min stack is currently not empty. So what we want to do is grab the minimum value. So we're going to do that like this. Length of min stack -1. So what we did right here is just we grab the minimum value. And let me actually zoom in so it's a little easier to see the code. But then what I'm going to do next is we're going to check if the minimum value is greater than the current value we're trying to push onto the stack. And if that's the case, then let me change this, because that's a reserved keyword in Python. But anyways, so if the minimum value is greater than value, then that means we have a new minimum value. So we must push that onto the minimum stack, or the min stack. So self.minstack.append value, so that becomes a new minimum value, and then out here we want to just add this value to the stack. So regardless of whether the min stack is empty or not, we want to push this onto the stack anyways. So this is what we did. So if the length of the min stack is 0, then we want to append the current value to the minimum stack, and then append the value to the stack also. Otherwise, we want to check if the value is less than our current minimum value, and if it is, then we want to append that value to the min stack. Cool. So that's our push method. Our next method is our pop method. And the one special circumstance, I guess, that I would think of in this case would be if the value that we're popping off is the current minimum value. So the first thing I'm going to do here is actually change this to a greater than or equal to, and the reason is if the minimum values are if the value is currently equal to the minimum value, we actually do want to add duplicates into this min stack. And I'll explain why in just a second. So we're gonna start this method off by checking, we're gonna start by popping the top of the stack. So we can do that like this. And then we're gonna check if popped is, or before I do that, I need to grab, I'm just gonna copy and paste it from here, but I need to grab the minimum value first, and then we're gonna check if the pop value is equal to the minimum value. And if that's the case, then we just wanna pop the top value off the min stack. So self.minstack.pop. And the reason why we're doing this is this current minimum value in the min stack, we need this to go away if it's equal to the popped value, because now that value doesn't exist in the stack anymore. And the reason why I have it so like up here where I said greater than or equal to val, the reason why I said greater than or equal to is because imagine that this is our stack and this is our min stack. So we first start on by pushing 5, and we'll push 4, because imagine that there wasn't this equal sign over here. What would happen is when we pop this 4 off, we're also going to pop the 4 off here on the stack, but our current minimum value is actually supposed to be 4, not 5. So we're adding duplicates into the min stack just to account for situations like those. So over here it says that pop should return none, because it returns void. So in this case, our pop method should be complete. So next we're gonna do top, and I mean this one's fairly straightforward. We're just gonna say return self.stack, and we're gonna return the value at the top of the stack. And then for get minimum, we're gonna do the same thing, except we're not gonna do this with stack. We're gonna do this with min stack and return self.minstack -1. So that just gets the top value on the min stack, which is just the minimum value. So let's submit this, and let's see. It says name min stack is not defined. Did you mean min stack? Let's see. Does it tell us? So this is line 11 in push. So that's over here. So the problem was I didn't put self over here. Now let's try submitting this again. Seems like I did that again somewhere. Let's see. It says line 19 in pop. Yep, I did it again. Now let's try submitting this. Perfect. So the solution got accepted, and now let's go over time complexity and space complexity. So as for time complexity, I mean, this question already said that each question or each function must implement a solution within linear time, and these are all within linear time. So as you can see here, we're not looping through any elements. These are all just constant time operations. Same with here, here, and here. And so our time complexity is just going to be linear time for every single method. I'm sorry. As for space complexity, this is going to be, oh, okay, I said linear, I meant constant. So the time complexity is going to be constant, but the space complexity is going to be linear. And the reason why it's linear is the stack at most is going to hold n elements, but the min stack can also hold at most n elements. So I mean in total that's 2n, but we're just going to say linear. So yeah, that's my solution for